In part 5, we're going to finish up IR by figuring out how we actually approach these infrared spectra. Okay? I'm given this spectrum. What are these peaks telling me? This video is all about practicing that. So make sure you're good with the previous 2 videos before we get into it. Okay? So let's start by looking at an actual labeled peak, or sorry, a labeled spectrum. This is for diethyl ether. So let's think about what we're given here. Okay. We see this big peak at around 1100. Okay? So we know that that tells me I've got a carbon-oxygen single bond. That carbon-oxygen single bond could come from a couple of places, like an alcohol would also have a CO single bond, but I don't have a big peak over here around 3400, okay, which is a really important concept as well. The absence of absorption bands can also help you identify a product given a spectrum. Okay. I also know I don't have a carboxylic acid, for example, because there's nothing at 1700 where that carbonyl peak would show up. Okay. I don't have any peaks above 3000, so I don't have any SP or SP2 hybridized carbons. So by process of elimination, I'm pretty much down to an ether. Okay. I don't know if it could be, diethyl ether or ethyl methyl ether, something like that, right? This is why we need multiple methods of analysis, but you see all that information I can get just from looking at an IR spectrum in terms of the functional groups. Okay. Now, one thing to keep in mind too, the absence of absorption bands can help, and also know that some vibrations are infrared inactive. Okay, so infrared isn't 100% perfect. What do I mean by that? How are things infrared inactive? Okay, which is an important idea to keep in mind when you're drawing these conclusions. Okay, if you go back to when we first introduced IR, right, that absorption of infrared radiation corresponds to a change in dipole moment. Okay, so if the stretching is not accompanied by a change in the dipole moment, then you don't get an absorption band. That's when we consider something to be infrared inactive. Okay, so for example, the CC double bond right here, we know that sp2 hybridized carbons, right, have a certain peak. But a symmetrical molecule here, when that bond stretches, which is what the functional group peak corresponds to, the dipole moment doesn't actually change because everything on the outside is the same. Okay, so we would get it for 1-butene. This would have an absorption band, okay, because there'd be a change in the dipole because there's a different group over here. But we wouldn't see it for an asymmetrical molecule, which can be tricky. But just keep that in mind. Infrared inactive vibrations do exist. Okay. So it's possible that you have a functional group that's present but doesn't appear in IR. Again, we need multiple methods of characterization. So let's jump into interpreting these things. We got 5 of them. Here's number 1. And again, we're not trying to get a perfect structure here. Okay, we're just trying to pull out as much information as we can, right? We should be able to determine, for example, what kind of hybridizations are present. All right. So let's first look over here. Okay? I've got these large peaks just to the right of 3000. That tells me that I've got sp3 hybridized carbons. Okay, good. And then this big peak right here at about 3100 tells me I have sp2 hybridized carbons. Okay. Now with sp2 hybridized carbons, I should, if those are corresponding to benzene, I would also see peaks at around 1600 and 1450. Okay. And I don't see anything at 1600. I do have 1450, right? But you have to have both of them together. Even if these were our 2 peaks, they'd be a little more intense. So no benzene. Okay. So really, all of my information is coming from here, plus the absence of peaks over there. No alcohol shown over here, no carbonyl shown over here. Right? So really no other functional groups to worry about, no amine, no aldehyde. And if you want to check your fingerprint region, this 890 tells you you've got a terminal alkene. So we just get to start to put together some of the puzzle, right? We have sp2 carbons. We know we've got a double bond somewhere. This tells us it's a terminal alkene, and we've got some sp3 hybridized carbons as well. We get some information from IR. Mass spec would help us put together more of the puzzle, and we would use NMR in the future to confirm it. Okay. And here's what this structure corresponds to, right? sp3 hybridized carbons, terminal alkene, pretty much the bulk of the information we can get. Again, noting the absence of some bands, meaning other functional groups I might guess at first, IR will tell me for sure they're not there. No oxygens, for example. How about number 2? Now, I recommend, right, that you pause these and think about them to yourself or check them in the Blackboard notes. Okay, do these for practice and then come back and watch these videos. So what's the first thing that pops out here? Well, 2 things if I'm looking at it, right? This giant peak at 1700, so I know that I've got a carbonyl, right? Then there's another thing that's really notably absent, which is the usual big peaks we see just to the right of 3000, okay? So there's no sp3 hybridized carbon peak, okay? But I do see a peak over here to the left of 3000 at about 3100. That tells me sp2 hybridized carbons. So now I think to myself, could it be benzene? Well, I've got some peaks at 1450 and 1600. Okay, so that tells me, yeah, I've probably got benzene. And then there's one other notable thing here, right? We said look out for 2720 and 2820. Boom, those 2 peaks right there. I've got an aldehyde. So that's a lot of information from this IR spectrum. You try and piece it all together, right? And our product is benzaldehyde. Again, everything that was, sorry, I jumped aside there. All of those peaks discussed below. Plus also note the absence of the sp3 peak. Number 3, what do I see here? Okay, first thing that jumps out, that huge peak, right? Tells me that I have an alcohol, that large, broad peak centered around 3400. That little peak pointing out down below at 3300 also tells me an sp hybridized carbon. You wouldn't get that sharp of an edge if it was just an alcohol. Alcohols are always rounded, so that peak poke, because it's 2 overlapping peaks, right? That peak poking through, sp hybridized carbon. Okay, and that triple bond is confirmed with a peak at 2100. Okay. Now over to the right of 3000, I do see some peaks here that are indicating I do have some sp3 hybridized carbons. They're not as strong as normal, and that's usual, okay, because when you have an alcohol, it absorbs so strongly that it kind of by default makes every other peak small, except for this one over here, which is corresponding to the CO single bond. Okay. There's no peak around 3100 for sp2 carbons, so I know I've got sp3 and sp plus an alcohol. Okay. What is the actual structure? Okay. Propanol right here. Okay, sp3 carbons, or sorry, sp carbons on the left, sp3, and the alcohol. Okay. Now it's true, there could have been another methylene, another CH2 in here, for example, right? But this is why we need multiple things paired together. Mass spec would give me the molecular formula, and then using the 2 of them together, 9 times out of 10, I can start to put together a really nice structure. Number 4, okay, what is poking out here? All right. Well, again, I've got, there's really 2 things I'm always looking at, right around 1700, right, and right around 3400. Okay, 1700 tells me I've got a carbonyl, but it's also shifted a little bit to the right. It's closer to 1660. And if you go back to our previous video, you say that's a clue that I've got something that's donating by resonance to my carbonyl. And the only thing we know that likes to do that is an amide. Okay, so I'm thinking I've got a C double bond O with an N right next to it. Okay. And the fact that this peak over here at 3300 is split, right, into 2 peaks tells me that I've probably got an amide with some hydrogens coming off of my nitrogen, those NH bonds that also show up in the same region of an alcohol. Okay. That is confirmed over here, right? 1560 gives you an NH bond. it's confirmed right there. And sure enough, right, everything that we see right there, in addition to my sp3 hybridized carbon peak, which corresponds to that methyl group right there. One more food for thought, a super obvious ketone right here. Sorry, super obvious carbonyl. This one does end up being a ketone, right? Notice it's right at 1720 where we expect it to be. Okay. What else am I saying? Okay, I look at 3000. I've got some stuff to the right. So I know I've got sp3, but I've also got some peaks to the left. Tells me sp2. Multiple peaks to the left mean I've probably got benzene. So I go over and I look at around 1400 and 1650, right? So I've got some peaks there that are confirming my benzene ring. Boom, boom. All right. So what am I dealing with right here? Ethyl benzyl ketone. Everything corresponding to the bottom. I want to make it clear you're not expected to look at an IR spectrum and be able to get, using nothing else, this structure. You will be expected to look at an IR, a mass spec, because remember there's some clues in mass spec for detecting functional groups as well, and a proton and a carbon NMR, that's coming from chapter 14, and then piece together simple structures. Okay? But infrared in the detection of functional groups is one of the critical pieces that goes into that.